All right, so hello everyone. Sorry for the little bit of a delay. Welcome to this presentation on eclipses and the search for other worlds. So as you all know, we do have an eclipse coming up on Monday. Hopefully it stays clear in Madison if you're staying in Madison, or otherwise even better, hopefully you're going to totality zone. So my name is Jaime. I'm a solar system ambassador on behalf of NASA and the Jet Propulsion Laboratory. I also am a PhD candidate in the genetics department in Nicole Perna's lab. How I ended up blending those two, I have really no idea. I just happen to both love space and genetics. So that's how I ended up here. So we'll talk a little bit about eclipses. We'll talk a little bit about how we use something very similar to an eclipse to search for other worlds. And we'll also finally talk about safety during the eclipse. All right, so there's a couple different types of eclipses. There's a lunar eclipse. There's a solar eclipse, and then my favorite, or the funniest one to me, an apocalypse. So obviously, a lunar eclipse is when it's moon, Earth, sun, which is when we get that kind of red moon. Solar eclipse is what we're going to see on Monday, and apocalypse is hopefully something we never see, where the sun is actually closer to us than the moon, which we'll see, but never know. All right. So what exactly is a solar eclipse? Solar eclipse, as I mentioned, is when the moon is moving between the sun and the earth during a new moon phase. So Monday will be, we're undergoing a new moon on Monday. And what happens is a shadow of the moon, is being cast on the surface of the earth. And depending on what plane the moon's orbit is in, it'll either partially or fully block the light of the sun. Thankfully for us, we are getting a fully block of the sun, which is why we get to see that total eclipse along that path of totality. Now, so for the total solar eclipse, for the eclipse in general, there are generally two different areas that we're able to see. So you've got the sun. If I can get this over there, there we go. So you've got the sun, obviously, you've got the moon, and then the point of totality is an area called the umbra. So that's the darkest portion, where you'll see the complete shadow of the moon. And then on the partial eclipse area, it's called the penumbra. So that's the rest of the much larger area that's going well past into northern Canada and well past into southern Mexico. Now, when exactly do solar eclipses occur? I spent a lot of time on this, so I hope you really appreciate it. So solar eclipses occur during eclipse season. So what exactly is eclipse season? So there actually is called that. So this is a time period when the moon, the earth, and the sun are all lined up on the same plane. So this generally lasts about 34 days, and it occurs roughly every 6 months, or right around the equinoxes. So you may ask, well, why is it that we don't have a solar eclipse every month? Well, as I mentioned, that's where the plane of the moon comes into play, or the moon's orbit comes into play. So as you can see here, moon is orbiting around the earth, got the sun pointed over here to our left. Because the moon's orbit is tilted, then the placement of that shadow is constantly changing. Sometimes it's a little bit too high, and as it continues to go around, sometimes it's a little bit too low. So there always is a shadow, but sometimes we're just not, our planet is just not in the right spot. I'd say if we were to go out into orbit, so well beyond the International Space Station, then we might be able to see a different type of eclipse, or a different eclipse. Now, there are different types of solar eclipses here in Madison. We'll see a partial eclipse, and partial eclipses don't just occur during if you're outside of the path of totality, but there are also times where it just doesn't line up properly, where there's any totality at all. So there's just a partial eclipse everywhere. Then there's an annular eclipse, which we had in October of last year. Wisconsin being Wisconsin, of course, was cloudy on a day of a really nice astronomical event. So we didn't get to see it. But otherwise, we would have seen this really cool kind of ring of fire effect. And then finally, we have total eclipses that we're going to be, that if you travel down to the path of totality, you're going to be able to see. Now, so a little bit about all of these different types. Partial eclipses. So with the partial eclipse, the moon is either nearly above or below in its orbit. So it's only covering part of the sun. Or this is what you would see before or after the total or annular solar eclipse. And this is, again, what you would see if you're outside of the path of totality or annularity, depending on what type of eclipse it is. Now, for an annular eclipse, the moon is, in this case, it's farther away from the sun, or I'm sorry, farther away from Earth in its orbit, and it is passing in the right spot between the sun and the Earth. However, because it's farther away in its orbit, it's not actually covering the entire disk of the sun. So let's go ahead and take a look real quick. So for a total eclipse, like we mentioned, you've got the sun, moon, Earth. You've got the umbra that it casts that dark shadow, and then you've got the penumbra that casts the rest of the partial eclipse. But for an annular eclipse, because the moon is farther away, then what happens is the penumbra is actually out in orbit. So if, let's say, for example, we had I don't know, a space station that's out in a certain altitude of orbit, then they would able to be actually see a total solar eclipse when we would be observing an annular eclipse. So the penumbra is there, and then on the other end is the antumbra, which is what we observe during the total solar or during an annular solar eclipse. Now, the reason why it's referred to as a ring of fire or an annular eclipse is obviously because of this thin ring that occurs, and it comes from the ring shape known as annulus. Now, the granddaddy of them all is, of course, the total solar eclipse. Is, of course, the total solar eclipse that have any of you been lucky to see one? I have. Saw it in 2017 out in Oregon, and hopefully, if it stays clear, we'll be seeing it again on Monday. Now, for total solar eclipses, in this case, the moon is closer to the Earth in its orbit, and it's passing between, again, the sun and the Earth, and it's completely blocking the face of the sun. A total solar eclipse occurs roughly, on average, every 18 months. Obviously, it's different on where exactly it's occurring, but on average, it's roughly about every 18 months. Now, following this eclipse that we're having on April 8th, then the next solar eclipse that will occur over the US won't happen until 2045. And in that case, it'll actually be going down from Oregon down through all the way down to Florida and the Bahamas. Now, one of the reasons why it's so cool to see the total solar eclipses, not just because it's beautiful to see, but also because there's a lot that we can understand from these total solar eclipses that gives us a unique opportunity. So during a total solar eclipse, it gives us a unique opportunity to understand and study the corona. So that is the outer atmosphere of the sun. It's over 1 million times fainter than the light from the photosphere that's on the surface of the sun. And so essentially it's impossible for us to see. Now, there are several spacecraft that essentially produce artificial eclipses, using what's called a coronagraph that allows us to actually study the corona. However, because of that type of artificial eclipse, the lower portion of the corona, the part that's closest to the photosphere, is actually blocked. So we're only really able to study that portion of the corona during the total solar eclipse, which is what one of the things that'll be happening during this upcoming solar eclipse. And I'll talk a little bit about some of the science that's going on with that shortly. Now, one of the interesting things is, like I said, so the corona, we can only study it so many times, and there's still a lot of mysteries from it. So the mystery of the corona is that the sun, we know, its energy is created in the core. That travels out through the radiative zone and the convection zone, and then it's transferred out radiated out into space. And as it's exiting the core, it actually gets cooler. So, obviously the photosphere would be cooler than the core. But what's really interesting is that in 2019, the Parker Solar Probe found that 2021, the Parker Solar Probe found that actually the coronas are hotter than the surface of the sun. Now, it's not necessarily clear why, but using the Parker Solar Probe, which is the closest probe that's ever attempted or that's ever gone towards the sun, and even then it's still millions of miles away. It's doing its closest approach in December of this year. That'll continue to study the corona and help us understand why it is that the sun's corona is actually hotter than the surface of the sun. Now, what types of eclipses will be seen on April 8th? So if you're again in the path of totality, you'll see this ring, the total solar eclipse. If you're outside of the path of totality, it's like here in Madison, we'll see a partial solar eclipse. Now, the totality will be seen through various portions, or I'm sorry, it'll go from the western and northern portions of Mexico. From there, it'll continue northeast through parts of Texas. Then it'll go through small portions of Oklahoma, Arkansas, Missouri, where hopefully I'll be, Tennessee, Illinois, Kentucky, Indiana, Ohio, a very, very, very tiny portion of Michigan, Pennsylvania, New York, Vermont, New Hampshire, and Maine, and then finally a couple of eastern portions of Canada. The longest duration will be at 4 minutes and 27 seconds, which is occurring in Torreon, Mexico, which is a northern city I'd say about 200 miles south of the US border. And along this path, there's going to be over 30 million, there's over 30 million people that live along this path. But there are a lot of eclipse chasers, so that's going to be, there's going to be a lot more than 30 million people going to this path of totality. Now, one of the really important things or one of the interesting things about the path of totality is that even if you are within the path, the closer that you are to the center of the path, that's where you get the longest totality. Once you start actually getting closer to the edges, then that number starts to decrease. So even if, let's say, you're in the place where it's the longest, 4 minutes and 27 seconds, if you're on the outer edge of that path of totality, then that number decreases to about a minute, or possibly even less. Quick drink of water. Now, some of the different things that we would see during a total solar eclipse is there's a couple different phases. So there's first contact, where in this case, the moon is touching the sun, and it takes its very first nibble out of the solar disk. So it's sort of like we're seeing right here. Then the really pretty part is second contact, where in this case, there's a couple of seconds where there's these kind of like bead-like lights almost that might be visible on the edge of the moon silhouette, or I'm sorry, on the edge of the sun. And the reason why that's occurring is because of the valleys and craters that are on the moon. So as the light is passing through, then there are a couple of portions where the light is able to break through, or pass through, I should say, and essentially gives this kind of bead-like effect. And finally, there's the total eclipse, where in this case, the moon is covering the entire sun. It'll last a couple of minutes, again, depending on where you're located within the path of totality. In this case, let's say it's 4 minutes, 27 seconds. Then you have third contact, where now the moon is continuing to move forward. You again get these kind of Bailey's beads, and you get that diamond ring effect. That's from thanks to the light passing through the moon's craters. And then finally is fourth contact, where now the moon isn't covering any part of the eclipse, and the eclipse is officially over. In this case, the eclipse for this Monday is lasting around about 3 hours and something minutes. Now, if you are in the path of totality, there's going to be a couple of things that you will see that I've already mentioned. But first, you'll see a red part around the sun. This is known as the chromosphere, and it's red because of the hydrogen gas that's coming from it. You'll also see this kind of diamond ring effect that only happens for about a second or two. Essentially, that's occurring as the moon is starting to finally cover up the sun, and you get this last little bit of light that's coming through from the valleys on the moon. And that occurs twice. It occurs at the beginning and at the end of totality. Then you've got Bailey's beads, where in this case, same thing. There's these kind of like bead-like structures that occur thanks to, again, light passing through a couple portions of the moon. And then finally, these really cool plasma strings, essentially, known as prominences. So these are made of really relatively cool plasma that are supported by these magnetic fields, and these can be as large as 2 to 3 Earth radii. They're extremely large. They're a little bit difficult to see with the naked eye, so if you have a telescope, again, then you should only be using during totality. If you're going to use it, then that's when you would actually be able to see that. Now, Madison will have about 89% coverage, starting at about 12:52 p.m. Oh. So it'll start at about 12:52 p.m. There we go. So to start at 12:52 p.m., the portion of maximum where it'll be 89% covered will happen around 2:05 p.m. And then it'll continue on until roughly around 3:16 p.m. or 3:20, where the end of the eclipse occurs. And here that maximum eclipse will last around 2 minutes. So, like I mentioned, you don't want to miss this if you can't, or if you can avoid missing it, then I would do that. Following this one, like I mentioned, the next one won't happen until August 12th, 2045. And if you're somehow able to live another 500 million years or so, then eventually you won't be able to see a solar eclipse, a total solar eclipse at all. And that's because the moon is moving away from us at a roughly, 3.8 centimeters a year. So eventually, and the math has been done, eventually total solar eclipses will be impossible because the moon will just be too far away. And that's about 563 million years from now. So don't worry about it for now. Now, there are a couple of different ways that NASA is going to be studying the eclipse. So including various solar satellites or solar focused satellites or solar focused telescopes, such as the Parker Solar Probe, which I've already mentioned. There's also SOHO and various NOAA missions. If you are not able to get to the path of totality, but you are interested in seeing the totality, NASA has telescopes all along the path of totality where they'll be live streaming. NASA and SLU and a couple of various other organizations will have those live streams. And in addition to that, there's a couple of other specific missions that NASA is focusing on. So NASA will be chasing the eclipse using these high altitude research planes. For you plane nerds, this is a Canberra, which there are very few of. So the planes will be taking observations using infrared and visible light camera. And basically what it's going to be doing is it's going to be studying a dust ring that's around the sun and looking for asteroids that may be near the orbit of the sun that we just can't see because they're so close. This W57 Canberra has cameras and spectrometers that'll be studying that stream of particles that's coming from the sun. It will also be observing, excuse me, there will also be observations of the sun's disk and the Earth's ionosphere from the ground. So from the Goldstone Apple Valley Radio Telescope, there will be studies to map the magnetic fields on the solar surface that are coming out from the solar corona, or that are going out to the solar corona, I should say. And in addition to that, there will be several ham. Oh, sorry. Actually, before I get to that, so there will also be a radar network that's going to be using radars to essentially study how the flow of plasma in the ionosphere. And then finally, there will be several amateur ham radio users who will be studying communication going through the ionosphere before, during, and after the total eclipse. Now, any questions so far? What does it do the other time? So then that Canberra, so it's studied it's used, excuse me, primarily for atmospheric sciences missions, or it'll also help during launches. So generally, anytime there's a SpaceX launch or eventually a Boeing launch or something like that, then the Canberra and other high altitude planes are helping with that. But this is just one of several planes that are in NASA's repertoire of planes. All right, so now these types of eclipses aren't the only kind of eclipses that we see. We also use eclipses to essentially uncover alien worlds, also known as exoplanets or extrasolar planets, and that's because these are outside of our solar system. Now, the way that we use eclipses, or in other words, or more specifically transits, is we use those to help us find these exoplanets. So essentially what's going on is we have a telescope, whether it be in space or whether it be here on Earth, that's observing a particular star, and it's observing it for a certain amount of time. And if there's suddenly a dip in the amount of light that's coming from that, excuse me, that helps us determine, or that tells us that there might be a planet there. Now, depending on how much light is dropped or how much light drops, that tells us a little bit about how large that planet may be, and it also tells us a little bit about excuse me, about how long it takes to orbit. Now, one of the really more interesting things, in addition to finding that, well, hey, there's a planet outside of our solar system. In addition to finding that, one of the ways that we use these transits or mini eclipses to our to the advantage of scientists is doing transit spectroscopy, where essentially what's going on here is at the same time that we're studying those exoplanets or looking for those exoplanets, once one of those becomes confirmed and it seems like it's an interesting candidate to study, then future missions, in this case, let's say, for example, the James Webb Space Telescope is doing these kinds of studies right now. We'll point the James Webb Space Telescope at this particular exoplanet. We'll measure, we'll use spectroscopy to measure the light that's passing through the atmosphere. And that will tell us a little bit about what the atmosphere of that particular planet could be made of. So for example, in this case, let's say we take Earth, then we see if someone's looking at us from, light years away, and they're studying our atmosphere, well, they're going to see these black bars along the spectrum that are telling us that there's some kind of absorption. In this case, there's ozone, oxygen, water, methane, and CO2. And in addition to, and we could do that for other exoplanets. So for example, in this case, then we're just seeing a bunch of methane. Now, one of the more interesting exoplanets is known as K2-18b. Now, the reason why this is really interesting is that it seems to be probably the most potentially habitable world that we found so far. And there's a couple of caveats to that. Now, the reason why it's called K2 is because it was found by the Kepler mission. The Kepler mission has since been stopped. Now, that mission is primarily, or the exoplanet survey missions is primarily being done by the TESS mission, and for future studies are being undergone by the James Webb Space Telescope. Now, reason why this is this appears to be the most habitable one is that in 2019 there was water vapor that was detected in its atmosphere, and then in 2023 there was a detection of carbon dioxide and methane and it appears to be rich in the atmosphere of this particular exoplanet, which can help us can help us to interpret what this planet might be, telling us that it might either have a water ocean or it could be a magma ocean planet, something in that vicinity, and that it would have a high hydrogen-rich atmosphere. Yeah, so this is a little bit about that carbon dioxide, methane, some of the things that we're finding that these planetary scientists have found. Now, the detection of methane in particular, along with, the detection of carbon dioxide with the shortage of ammonia that's present here, then that tells us a little bit that there could be a liquid ocean there underneath like I mentioned, a hydrogen-rich atmosphere. We'll never know. K2-18b is 110 light years away, which means it would take us thousands, if not millions of years to ever get there. So we'll never know, or we'll never be able to fully confirm if that is a habitable planet or if there is life there. But for now, we can just interpret whether it might be habitable or not from our place in the universe. Now, one of the problems with K2-18b is that it's not necessarily clear if it has a rocky surface. So it has a hydrogen-rich atmosphere, but because it's not really clear if it has a rocky surface, well, if there's no rocky surface, then that means there's not necessarily somewhere for life to potentially originate. Now, while it looks great right now, it's not entirely sure. And it's not entirely sure if it is the most habitable planet. Now, with regards to transiting a little bit over to life, or the search for life, I should say, there's a couple of different ways that we look for these exoplanets and how we determine whether they're possibly habitable. One of the methods is known as the habitable zone. I don't really like calling it the habitable zone. It probably should be more called or most people call it the Goldilocks zone. Essentially what it is it's an area where water can exist in a liquid form. If you're inside of or within the habitable zone, then it's far too hot. Liquid water just evaporates. If you're if you're in the habitable zone, which like us have liquid water, if you're outside of that, then it's far too cold. Now, What's interesting is that the habitable zone depends on a couple different things. It also depends on the type of star. So for example, our sun is a G star, so it's medium sized roughly. And we have this particular habitable zone. But once you start getting to different sizes of stars, that habitable zone can either extend way far out there on our own orbit, or it can actually be even much closer. But even then, even if it is within that habitable zone, that doesn't necessarily mean that this particular exoplanet is actually habitable, because it would also need, at least we estimate based on life as we know it, a rocky surface. It would also need an atmosphere, and it would have to have a certain type of atmosphere, because if it's too much, if it's too gaseous, then it's not stable enough for complex molecules to form. It has to be the right size, and there has to be enough time. And what I mean by time is that sometimes these really hot stars, well, and they end up burning out quicker. So if these large hot stars are only lasting a couple of million years, then that's not enough time for, at least based on life as we know it here on Earth, to actually arise. So just because these exoplanets and the way that we find them just because these exoplanets seem habitable, doesn't necessarily mean that they are. Now, using this transit method is actually the way that we found most exoplanets. As of last week, that number is about 5,599 exoplanets, with most of them having been found through that transit method. So that's that green bar right there. And as I mentioned, 5,599 exoplanets are confirmed. There are tens of thousands of candidates of exoplanets that have yet to be confirmed. And in addition to that, astronomers believe that for every star that's in our universe, there likely is at least one exoplanet. Now, that doesn't necessarily mean that every star is going to have one. We've looked at, or planetary scientists and astronomers have looked at certain stars. They don't find an exoplanet there. But that just tells us the huge number of exoplanets that are in our universe, which is a possible place where life could potentially arise. Now, in terms of the future of these exoplanet studies, so far, it kind of really started with Hubble. Or I'm sorry, I should say it started with ground-based observatory studies, which the first one was found in the early 90s. And now we've already gone to close to 6,000. Went on with Hubble. Most have been found through that Kepler K2 mission. Now it's, excuse me, TESS, which is surveying the entire sky to look for exoplanets. And then the James Webb Space Telescope, which is doing more detailed characterizations of those exoplanets after finding them through those transit methods or various other methods. And the European Space Agency has a couple of missions that are coming up that'll continue to study these exoplanets. Now, so we can't look at a transit or a tiny eclipse on another exoplanet, but we can obviously see a transit or an eclipse here. So how are you going to watch the eclipse? If you are, there's a couple different ways. Hopefully you all have your eclipse glasses. If not, there's a couple over there that you can feel free to grab. Or you can also use what are called pinhole projectors, which essentially in this case, you're essentially using it's a tiny hole and it's projecting the shadow of the shadow of the sun onto whatever surface. You don't necessarily need something fancy that's 3D printed like this. You can even do it with your hands, or you can actually also do if you're standing next to a tree, the shadow passing through or the light passing through the tree will create thousands of little shadows of the eclipse occurring right on the floor. Now, so that's anywhere. If it's partial or if you're in a path of totality and it's a partial eclipse, or if you're not in the path of totality, then you want to use these guys. If you are in the path of totality, excuse me, you want to use, again, those solar eclipse glasses during the partial, take them off during the total eclipse, and then put them back on during the partial. You have to use solar viewing glasses. You cannot use regular sunglasses. I'm sure you guys all know this, but I'll say it anyways. And you definitely cannot layer different sunglasses over each other. I've heard people doing that. You don't want to do that because it's just going to destroy your eyeballs, and you're going to end up with a nice eclipse burn on your eyes. Now, really the only types of eclipse glasses that you should be using They should meet a certain standard. So it's the ISO 12312-2 standard. Again, there's some here. These are straight from NASA. I recommend getting some if you don't have any yet. If not, then you're also welcome to get some at a local library. I know that they started giving them out as well. It's cutting it close, but I would not recommend ordering them from Amazon because anyone can go on there and sell it. Doesn't necessarily confirm that they are the safe ones. And again, it's going to reiterate, 99% is not the same as 100%. Anything less than 100% is a partial eclipse, and you have to use those solar eclipse glasses the entire time. You can't, so even if it's just kind of this little sliver, it's still going to be extremely bright. And once if it's actually 100%, then you can actually take your glasses off for those 4 minutes and however many seconds. And like I mentioned, there's different indirect viewing methods using pinhole projectors, or you could use a colander. You could use your hands to look at the to view the shadow of the eclipse, and you can also project either using a telescope or using a binoculars. Now that doesn't mean look through them, but essentially you could set it up and it's projecting that light, and you would put it a certain distance away, and you could see the eclipse, or sorry, see the shadow occurring on like on your hand or on a sheet of paper or something like that. There's a lot of instructions to do that on NASA's website to get more information on that. And then finally, now there are a lot of ways that you can contribute. So NASA is doing several citizen science projects during the eclipse, including looking all around you, seeing what changes as the eclipse is going on. If you've never seen one, I can tell you that it's going to suddenly start to get a lot colder, or a little bit cooler. The birds are going to suddenly get quiet. You know, if there's crickets or something like that, those guys are going to start chirping. It's very interesting. So there's various citizen science projects that you can contribute that will help NASA in the studies of these eclipses. And with that, I'm happy to take any questions. Thank you. Yes.
Question. What are the glasses made of?
So, oh, that's a good question. So those glasses, they're made of a, can't remember the exact material, but essentially it's a film that blocks 99% of light. I know I just looked up what the actual material was, but I'm forgetting it. But yeah, it blocks out 99% of light. You can also technically use welder's glasses as long as they're shade 14 or 15. But the thing you don't want to do is you know, those glasses, or those eclipse glasses, they have a special film that are mostly meant just for your eyes. You can't necessarily put them in front of a binoculars and use that. That you would need something completely different. Yeah.
Does the quality of the pinhole matter? I used to make, kind of for like images.
Yeah.
I really want to find a pinhole with no bird, but this is just sort of a shadow.
Yeah, I mean, honestly, when I tried it back in 2017, I know I just kind of just like poked a hole in a piece of paper, and it didn't work out that great, but it's still, I was still able to see the shadow. So it doesn't have to be precise, but I'm sure, you want to get a decently made. But again, you could do it with your hands. You could look using a tree. You don't have to necessarily use a precise pinhole projection. So.
What's the weather out?
Weather outlook. So here in Madison, I checked before coming over here. Not great. So it might be a little rainy. Hopefully it clears up by noon. And it all really depends. If you're farther down in Texas, which ironically is where everyone thought was going to be the best, right now it looks like it's going to be very cloudy and possibly rainy. As you start moving forward farther northeast, then it starts to clear up all the way through Indiana, up into New England, and then there's portions up there that also might get rainy. But right now it seems like it's going to be pretty clear throughout the Midwest. So, or at least within the path of totality, so I should say. I'm not going to Carbondale. I am likely going to just west of Carbondale, just to avoid the traffic. But yeah, just going just west of Carbondale through just past Missouri. There's a small town called Cape something. Cape, something with a G, I forget it. I looked it up last night. That, yeah, that's where I'm going. So I could look it up real quick. I am driving down. I'm driving down. Give me a sec. Yeah, Cape Girardeau. It's right along the Mississippi, just past or just into Missouri. I am driving down. If you are driving to the path of totality, I recommend that you leave Saturday or Sunday. Don't recommend leaving, you know, early Monday just because of the amount of traffic that there's going to be. So yeah, if you could do that, awesome. If you do decide to leave Monday, then hopefully it's Monday at like 3 a.m. The closest to us is Carbondale, roughly, which is about 6 to 7 hours from here. So yeah, just strongly recommend that if you're going there to leave early and have plenty of gas, because all those smaller towns are essentially on emergency status because of the upcoming eclipse. In a way, yeah, especially with that earthquake this morning. Yeah. Oh, that's a good question. I think it's just I mean, I would argue that if you are in the path of totality, then it's much darker than even with the cloudiest of cover. So I think that's more than likely what it is. I mean, even if it's cloudy, you know, and if it's a storm, yes, it gets dark, but it does not like night. Which if you're in the path of totality, it's essentially like night. You can see the rest of the stars that are in the sky. In fact, I forgot to mention that you'll actually be able to see all of the 7 observable planets. I think Neptune is the only one that you won't be able to actually see. But you'll actually be able to see all of the planets in a line across the sky. Might even be able to see a comet. I wouldn't recommend looking for it because it's still too far away to get a really decent view of it. But to answer your question, I think that's the main reason. Yeah. Well, there's no more questions. Like I said, there's Eclipse classes and there's a couple of other NASA goodies over there that you're welcome to have. I'll be here for a couple more minutes and I'm happy to answer any questions that you may have, whether it be regarding eclipses, exoplanets, or eclipse safety, things like that. So yeah, and thank you all for coming. And hopefully clear skies.